Okay, we're rolling. So we're gonna. I'm just gonna kind of leave it to you guys to do your attendance survey now, especially you're in advanced class. Assuming you want to be here. So if you think of ticking the box on that, it's great. It just helps me know you're here. And hopefully I kind of know everybody well enough now that you don't need me to call out your names. Let's jump into our announcements and then get going. We got our homework 2 and quiz 2 tonight. So don't forget those, especially the homework 2. You probably know the policy on quizzes. Those I would like everybody to turn those in on time because we just got to keep rolling forward on that. So please do your best to get that stuff in. And hopefully it's not too much. Friday, we've got a binary heap array lab. We're going to go over that today. So that's due on Friday. Not hard to do. It just sort of anchors our lecture for today. And then we will look at a recursive one on Thursday. But just give me tomorrow morning to double check this before you dive into it. Last year, I think we ran into a problem and I think I fixed the code base, but I want to check it in the morning just to make sure. So I don't send anybody on a wild goose chase. I think there was like an impossibility in that one, and people were working really long and hard to try to solve that. So bear with me tomorrow morning, and I'll send the all clear. 2 weeks, we got a implementation of the priority queue that we're going to talk about today. But we're going to do it sort of the brute force way, as a way of exercising our singly linked list management. So it'll be a way to make sure we all understand what a priority queue does, and to also just kind of skill up a little bit on managing linked lists, which we all really should have kind of handled by now, but we could always use a little bit of practice on that. And then our quiz 3, which will cover these 4 lectures as well. So that's what we got coming up. Today, we're going to dive into discussion around the priority queues, which is an abstract data type, or ADT. I'll use that abbreviation from time to time. It's an idea with an interface, much like, a black box. We don't know how it's going to be implemented on the inside, but today we will learn that heaps are a data structure that can be used to very efficiently implement this idea of a priority queue. So that's kind of our hidden data structure on the inside. And then we just have sort of the inputs and outputs like we talked about last time. So there are 2 kinds of priority queues. We talked about min and max. They always give us the most important or least important thing. And there are, of course, corresponding kind of heaps, min and max heaps, that go along with that. They very often seem like the same thing, but one's a data structure and one's a abstract data type. Seems a little bit like vague sometimes, but we'll show you the absolute differences. And we're going to introduce this idea of a binary tree, which we will get to know very well during this course. But this is kind of a mini introduction before we kind of explore some other avenues. We'll come back to binary trees a little later in the course. But this is a great way to start to wrap your head around what is a binary tree. We've kind of thought about it abstractly in terms of recursion and divide and conquer. But here we're going to start coming up with a data structure that persistently represents the idea of a binary tree. And we'll explore a few of those. And then we'll briefly introduce our homework 3 and then jump into our lab 9, which shouldn't take us too long today. So I don't think we're looking at a really huge lecture for you. Okay. So really quickly, three little purple slides. You're going to start to see me doing something like this. It's a little hacky, but I know I write a lot of code that flies around really fast. And this is a pretty machine independent way of putting a pause in your code. So you can always comment this out. You can just say, go to that cout, or or just put a return in it. But it's there so that we can slow the process down and illustrate what's going on. If it gets to be annoying, just kind of go, short circuit that and get it out of the way. If you do it all inside of the function, then you don't have to go change, all of your code. You can just keep calling the my pause. And this is probably how we'll end up seeing that show up. Okay. Remember from last time, we talked about our stack linked list, which was not really, a really brilliant idea to implement. Stack linked list. Sorry, that one was good, right? We're doing a normal linked list. via a stacked object with push and pop. And we're just going to keep following this pattern. We'll sort of encapsulate our algorithms or the data structures we're talking about in a class, and then bury all of their pointers and private data members inside. Now, you're going to see out on the internet, there's lots of ways to implement these things that are not part of a class. You don't have to do it in a object-oriented class-based way. You could just do it in a functional approach. For most of our stuff, we're going to wrap these things inside of a class so it's just easier to refer back to them over time. So we saw that last time. And we're also gonna, talk about things in a more prototype form, but the expectation is that you'll come in and remove that semicolon and replace it with some guts, all inside of your main.cpp. Okay. Q linked list was, another one we looked at. Very similar approach. I won't kind of go into all the details of that again, but we're just going to keep following that pattern and building up lots and lots of more classes. And I'll probably try to give you a little index card toward the end so you kind of know, which of these you've looked at. But let's talk about priority queues again. A quick introduction. Remember, there's a min priority queue and a max priority queue. As far as the abstract data type goes, it doesn't really specify how it happens. It just means that we should be able to ask for the least important thing and get it to come out. And these abstract data types are great for real-time data. When stuff is flying at you faster than you can process it, like let's say way faster, but you really just need to always be working on the most important thing or the least important thing. How do you do that, right? How do you keep up with this, data flying at you and sort through it or not sort, just sort of get the most important thing? That's what the priority queue is all about. When we really don't have time to look at everything and everything is changing all the time, right? So we're going to end up pushing into the bottom and popping stuff out of the top, right? So same thing with the max. It's just we flip the priority to be the biggest thing instead of the smallest thing. And these could be instances of a class that have all sorts of data in them, not just their priority. They could have a person's name and their social security number and all that stuff, right? So we could be prioritizing based on any arbitrary attribute, assuming these are instances of a class that we're kind of managing inside of this data structure. So very often we boil it down to just an integer, but really these could be kind of a last name or anything that we can, compare against the other nodes that are in our priority queue. Okay. So that's our min and max idea. And this is probably a pretty good interface. There is something called an indexed priority queue, which we will not cover in this class except to mention it. And that is a very special variation on this that allows you to change the priority of something that's already in the queue. So that's a pretty cool little animal. So in other words, you put it in there with a low priority, and then suddenly, somebody starts falling over in the line at the hospital and their priority becomes higher, right? So there is a variation on this that allows you to do that and still maintain all of the top end performance that this data or this abstract data type gives us. We won't explore the index priority queue here, but I will mention it as we get a little later in the course. So here's how we want to lay out our class. So we haven't really specified the implementation, but this is just our interface, push and pop, get size is empty, all that, typical stuff that, we have for most of our stuff. So the question is, how would we do this, right? And we're going to look at a couple ways. Homework 3 will be via a linked list, which is a pretty blunt, instrument for doing the priority queue. We're going to show you the super efficient way, which is so widely known, it's really kind of pointless to sort of have a homework wrapped around it, which is why we do this, in homework 3, the sort of not so sophisticated way. But we are going to need a node class to sort of connect all these pieces together. So we'll be dealing with 2 classes whenever we're working with our priority queue most of the time, especially for homework 3, okay? So as I mentioned, the priority queue is separate from its data structure, and there are lots of data structures we could use. We're going to study the binary heap, in particular, the binary heap array, and we'll show you what that means. But there's some other pretty interesting ways to go about doing this. And your homework 3 is kind of up here in the unsorted list area, although you'll have the opportunity to try to make that go faster in a variety of ways. But we're going to look at the binary heap today. So heaps are a data structure that can be used to implement the priority queue. And you can also jump into Program IZ Pro. There's a DSA is the acronym. I think most of you know this. It stands for Data Structures and Algorithms. So there's C++ course on that for those of you who have signed up for Pro and kind of had me expand your permissions. You can dive into that and look at this, from a different perspective, which, is always a good idea. But let's take a look at how we represent a heap in a binary tree structure. So here the goal is to have the least, in this case, important thing on the left-hand side of the screen at the top. So 1 is, of course, the smallest value. And below that, we kind of see a jumble of other numbers that are kind of in order, but not sorted in any way. So this is not what we would necessarily call a binary search tree yet. We do know that we are guaranteed here to have the smallest item on the top, and then the other way, on the other side, the largest item on the top. And some of you might sort of notice that one attribute we see, and we'll talk about it, it's called the heap invariant, is that in a sort of recursive way, every subtree follows the same rule. The biggest thing of that tree, that subtree, is going to be at the root. And so that is what we call the heap invariant. Means we cannot break that law. And if we follow that law everywhere recursively, then we have a heap, right? A valid heap, either a min or a max heap. Okay. So that's what we want to have. And it is, again, it's not a sorted structure. And our hope is that that might save us some time with our strategy so that we're not wasting time sorting everything, because all we really care about is finding the biggest or the smallest thing. Okay. So we'll say that our parent node, in this case, is going to have at most 2 children, but it doesn't necessarily have to have any children. So we could have some, theoretically null pointers pointing to these. And you may notice also that we're going to deal with a situation where the bottom row is left justified. Okay. So if there's any gaps in the tree where it's not completely filled out, it has to happen in the lower row to the right side. And we call that a complete binary tree. It's kind of a seemingly arbitrary name, but that's what they are called in the business. It's a complete binary tree. And that means it's it's got no gaps in unpredictable places, but it may not be perfect, right? It's actually mostly filled out, but not entirely filled out. And this is the data structure we're going to use, okay? So high level, it's a tree-like organization that satisfies the heap invariant, or our heap property, okay? It doesn't mean we have to store it using pointers, as we're going to see in a minute here. This is a very friendly way to organize data. We can actually put it in an array, which we'll see here in a minute, okay? So we could do it in a tree, we could do it in an array, we could do it in a couple different ways. But basically, it's a binary organization of data. Okay, so we have our max and our min heap invariant, as we mentioned, and we can have duplicate values. So whenever we do analysis and algorithms, especially when we're talking about binary trees, one of the questions we ask ourselves is, are duplicate values allowed or are they not allowed? So in this case, yes, we can have duplicate values in here. It's obviously a very useful thing to be able to do. Okay. So again, not a data structure, or is a data structure not an abstract data type, the heap, right? That is a structural thing, okay? So let's take a look at a little bit more generally, though, to make sure we know the neighborhood of the binary tree. So we're going to go deeper into binary trees, but there's lots of different kinds of binary trees. So, of course, they have at most 2 children. And if they don't, then they either have 1 or 2 null child pointers or null references. Okay. So there's a lot of variations. One is the binary search tree, which means that the order of the nodes throughout the entire tree is in what we call in-order traversal. That means the smallest thing is to the left at the bottom, and the largest thing is to the right at the bottom. And how we get there is a special traversal we'll look at again. We probably mentioned it briefly when we were talking about recursion. Okay, so that is the very specific kind of binary tree. We're going to deal with, one that is not specifically a binary search tree. It's actually just a binary tree or a complete tree. Okay, so all of these are, binary trees, even though they're missing some children. Okay, they are not necessarily complete binary trees, right? So these null pointers over here are just kind of implied a lot of times in my diagrams when we're talking about binary trees, even though I may not always show you those things, okay? But you could have a binary tree that's very unbalanced. It's missing a bunch of children on the right side there. And that's not really a great thing, right? We'll see later in the course that we want to avoid unbalanced binary trees like that, right? So they're not all heaps, right? And they're not all binary search trees. There's just some various flavors in there. But the complete binary tree is the one we're interested in. So here's some examples to be really clear. That is a complete tree. It's also called a perfect binary tree. So the word perfect implies the bottom row is filled out. Doesn't happen very often in real life, except in some maybe specific situations. But the complete ones have all the rows filled except potentially the last one could have some gaps. Okay, so that is complete. And that's an okay thing, as we'll see, for doing the abstract data type priority queue, implementing it via a binary heap. Here's another one that's okay. Okay, so that's what we mean by complete, even though the bottom row isn't complete, sort of, implies that it is. Okay, it's going to be left justified, if you will. Okay. So just for clarity, these are not complete binary trees. That one is missing a child, right? These are missing a whole bunch of children, right? They're binary trees, just not complete binary trees, okay? And not duplicate binary, or not perfect binary trees, okay? All right, jump too fast, okay? So that's the concept. Now, how do we kind of mush these two ideas together, okay? We could do it with pointers. Perfectly fine to represent a heap with pointers, but because we're dealing with this special case of a tree, it is very convenient to squash this thing into an array, okay? So we'll be doing lots and lots of pointer stuff down the road, but this is one of those few times where we can kind of get away with the arrays. So take a look at this flattening that we can do here by putting the root in the 0 position and then doing what we call a breadth first traversal. So a breadth first traversal is 9 and then go across the rows. Just that simple. 9, 3, 1, 0. 9, 3, 1, 0. So if we follow a breadth first traversal, we can treat every array, as a tree. We can sort of pour water on it and sort of reconstitute the tree from that flattened array pretty easily because the rules are actually not too complicated, as we'll see here in just a second. Okay. Now, if it's an incomplete binary tree, it means that we may have some extra unused array space over here, right? There could be some blank parts of our array that are ready for us to fill up. I've kind of just left those off the screen. But for what we have there in the tree, we really only need four slots to represent that thing. Okay. So there's our root, left child, right child, and then a left child of the next level down. Okay. And we'll look at the very simple math to actually figure that stuff out. Okay. So those are great for our purposes. So how do we find the child mathematically? It's not too hard. So from position 0, we're going to, move 1 and then 2 over. From position 4, we just are going to multiply the parent's position times 2 and add 1. So if we're talking about 4 as being the parent, 0, 1, 2, 3, 4, that's the 6, right, over here. The children should be 11 and 7, right? So that should be 2 times 4 is 8, plus 1 should be 9. There's our 11, right? And 1 more gives us a 7. So the rules are pretty simple, okay? Right? Simple plug and chug of our parent position to get there, okay? So we can traverse down the binary tree very quickly in terms of code execution by just doing some very simple integer math, okay? And probably the integer math is going to be, not even 64-bit math. It's going to be something smaller most of the time. Okay. Now it is possible that we might fall off the end of the array. So we do have a little, important check that we have to do to make sure we haven't gone too far, because otherwise in our code in C++, we'll end up just, grabbing onto some, illegal memory out there and using it. So the reverse of that, really pretty straightforward with a fun little trick. So if we know these are the equations for finding the children, we can obviously invert that. And the parent position of the left child is going to be left child position minus 1 over 2, right? So if I know that the left child is 11 over here in purple, I can get back to its parent, okay? 11 minus 1 over 2. And the right child is minus 2 over 2, but as a fluke of integer math, it turns out that we really don't even need to worry about minus 1 or minus 2. We can just say, whatever my position is minus 1 over 2, and it's going to get me to my parent, whether I'm coming from the left or from the right child. And that's a really nice little trick, because if you drop in the middle of an array and you're like, I need to get to my parent, well, how do you know if you're the left child or the right child? Well, fortunately, you don't need to know. You just apply that and use integer round off, and it should get you back to your parent. So we can move up and down the tree, right, pretty easily with these simple equations. And that is very much kind of what our lab today is about, is just getting a little bit comfortable with that. Okay. But let's take a look at, the breadth first traversal, just so we're all clear on what that is. If I were to give you a quiz question and say, hey, what's the array representation of that tree? All you'd have to do is just sort of, walk across those things in breadth first traversal, okay? Now, doing this in code, we will see here, is not always the easiest thing to do, depending on your data structure. If we were storing it with a bunch of pointers, right, in memory that are all connected together, doing that kind of traversal is a little different than what you might expect. But because we're dealing with an array and we are storing it always in breadth first traversal, it's really simple. We just sort of walk across the array from 0 to the size of the array, and that's our binary tree. Okay. So important to understand what a breadth first traversal is. It's one of the main traversal kind of things we'll be using for our binary trees going forward. But in this particular case, it's relatively easy to do in code, right? Because we're just walking across the array. Okay. So not a fully sorted tree, again, just partially sorted, you might say, or kind of semi-organized. And the same thing with our max, right? We're just going across the rows. So I might ask you, hey, how do you convert that into an array? Or I might ask you to go backwards and say, how do you convert an array back into its tree representation? Okay. So in order to do that, you really just kind of walk across and build the tree gradually. Okay. So we'll see some of those questions coming up. They're not hard, but obviously we have to remember, all about this breadth first search thing. So let's take a look at some interactive tools we can use. So over in the visualgo.net, there are some fun visualization tools over there, and we'll take a look at the heap visualization. Okay. And so you can kind of go at this any way you like, but I'll try to, bring out a few key points as we go through it. So feel free to explore as we go through this, but I'll kind of take you through some key points on a couple of these, practice problems. So there's no coding involved here, just sort of getting used to stuff. So let's just jump over there and let's see if we can build a small preset heap. And we'll do a max heap to start out, because all they do on this side is a max heap. We'll kind of come back to how we create a min heap without too much trouble. So over here, here's a very large tree, but let's start from scratch and let's create something where if I say create order n log n and I say n equals 10. So let's just start small. And I say create random. And I got my speed meter turned all the way down here. So you'll notice there's some switching going on here. So when we put in any new nodes, we put them in at the bottom row of the tree and then we bubble them up. So into their correct position. Sometimes they just land in their correct position at the bottom, but other times we have to kind of figure out how far up they got to go. So this switching that you see here is what we call bubbling up. And this is a technique that we use in a number of different algorithms. And all we're really doing is saying, hey, what am I like compared to my parent? Because if it's a max heap, then I should not be smaller than my parent. So I might need to swap my parent with me. And then once I do that, I continue again until I get to the top. And so every time we add something, initially it's going to fall in this area over here. Then we have our bubble up process, which is not super articulated here, but it's actually pretty simple once you kind of see it a few times. Now you can go in and insert something. So let's say we want to insert something with a particular value that is bigger than the 96. So let me go to 97 here, and you can do whatever you want here, but I'm just going to show you that process one time before we move on. Oops, try that, 97, okay, and then go. So it's going to land over here and then of course slowly make its way to the top, switching with everything. And that's going to ensure our heap invariant stays good, okay? So that's our basic construction of it. And given all of our conversations about divide and conquer and log base 2, there's one thing that should start to ring a bell in your head here. You'll be like, oh, this is kind of good because the maximum depth is always going to be log base 2 of all of the nodes that I have in my binary heap. And that means that the bubble up process is only going to do a maximum swaps of log base 2 to get the tree back into balance. And that is really where we gain a lot of efficiency with this kind of a data structure, right? We automatically, every time we push, the maximum is log 2 of n, okay? For this particular binary heap, right? There are other Fibonacci heaps and other kinds of heaps we could design, but that's how we can kind of quantify the worst case scenario. So it might not always go all the way to the top, right? So worst case scenario is if it has to go to the root. Obviously, if it's something like a 56, let's see if we can do a 56 here. We should have kind of a limited bubbling of this thing, right? So that's just going to go there and we're done. Okay. But our worst case is going to be log base 2. And that's the key takeaway and the advantage of this particular thing. Okay. So not sorted, but semi-sorted. Now, how would we do a minimum heap? Well, one way that we can simulate a minimum heap without even changing any code is just to agree that all of our positive values are going to be entered as negative values, okay? So we force everything to become a negative value when it goes in, or we negate what it was when it goes in, and then when we pop it out, we negate it again. And just that process, as you can imagine, if it was 100, it becomes a negative 100. So what's going to bubble to the top is the 0, right? The positive value. And then we just flip that thing when we pull that out. That is a pretty common trick that people use so that you're not writing two different kinds of heaps. You're just sort of mushing the numbers on the front end a little bit, okay? So there's probably somewhere places where that, isn't ideal, but for most of the times we can kind of get away with that. Okay. So if you think about it, if you have to create a tree of size n, we're going to do n log n insertions in the worst case. So we would say that to create a tree of size n, we're going to end up doing that bubbling process n times. And that bubbling process costs us log n. So that means that the creation of this thing is, in this particular case, 1 by 1 by 1 is going to be n log n. Okay. Now there is a linear way to do this if you have all the data already in an array. But we're talking about just sort of randomly picking a number out of the sky 1 by 1 by 1 and pushing it in there. And we'll come back to the linear one a little bit later. But that's our kind of key way of actually doing that. Okay. So you can kind of play around with that a little bit. There's a few other key things that I wanted to show you. But let's just remind ourselves that, we got everything below a 9 at that level, and then everything is guaranteed to be below an 8 at that level, regardless of the left or right side, etc. So that is our heap invariant in the case of a max heap, okay? And similarly for the min heap. And I say less than or equal to because we're assuming that we might have some duplicates in here, and that's okay. So there's our kind of key. So this obviously, it's really easy to get the maximum out of there all the time. So we'll talk about now, what do? We want to pop something off the top. So we were building a moment ago, but now we're going to talk about extraction. Let's look though, I know we saw the animation, but since I have the slides here, let me go through this just kind of on the slides to make sure we all got it. We always have space at the bottom. Okay, now yes, we might need to double the array size or grow it in some way if we're using an array. So there is that problem, but assuming that we can reallocate and make things bigger, like we did with our earlier implementations, we can assume we got a spot, and then we just got to do that swap. So if it violates the heap invariant, we'll do the swap through our bubbling until we get to a place where we want to be, and we're done. Some people call this swimming. Some people call it bubbling. So those two phrases tend to get thrown around a little bit. Bubbling up or bubbling down. Okay. Okay. And there's our invariant. And obviously, doing it over here does not break anything on the left-hand side. So we've isolated any impact to the rest of the array, which is really good. So there's our tree. Now, if we think about this, the number of swaps, of course, is going to be that log base 2, right? In terms of our comparisons. So bubbling up is a pretty straightforward process in that sense. We'll see that removing something is a little bit different, okay? So if you want, I think we probably covered this reasonably well the last time I brought this up, but see if you can, convince yourself that once it's full, it's going to automatically create a new row. So you might want to try, getting yourself to a full tree and just getting familiar with some of the realities of binary trees. One of the interesting things is the last row equals the total population of every row above it, right? So that is an interesting kind of realization of the binary tree. Like you're going to always be doubling on the way down. And so therefore you kind of have, actually, have I said that correctly? So let's do this, right? So insert 84, and we'll do it again, right? Insert 84, and then one more, 33. It's nice that it does it randomly. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. I'm missing something here. 1, 2, 3, 4, 5, 6, 7, 8.
It's always one more than the sum. Yeah.
Thank you. It's one more than the sum. Thank you. I was off by 1. Thank you, caller. Yeah. Yeah. So we can use that, and we will use that down the road, actually, to kind of size up the cost of adding new things. So in any case, I think this part is, probably, clear enough, but go back to that heap invariant if you want a little bit of practice on it. It's actually a good website for doing that. And feel pretty comfortable that within a plus or minus 1, even with some exact, math and some ceiling functions, we can figure out our worst case scenario pretty easily in code. Okay. And that's going to be our log base 2. Now let's talk about pop. So popping is not too much different. So we want the thing on the top the majority of the time, right? There is an idea that you could pull something out of the middle, but most of the time we just want what's on the top. So the way we do that is we just swap it with the rightmost lower leaf, right? And then we do our bubbling, right? So we want to get rid of the 9, right? So we're going to put it where the 4 was, and then sort of officially reduce the size of our array that we care about, okay? We might not deallocate the extra space of the array, but we'll treat that 9 slot like it's no longer got anything in it. It's now sort of garbage data, and we can use that later if we add stuff. And now we want to just do our bubbling down. So we want to first find the largest child of number 4. It's going to be either the 8 or the 7, okay? So we kind of have an extra step here that we didn't have bubbling up. We got to figure out, are we going left or right here, okay? So we pick the biggest thing, and we sort of attack that, and we sink or we bubble down or swim down, okay? And we just keep going until, you know, we get to the bottom, or we no longer have to do any swaps, okay? So we got to take the 4 down over there, and eventually we get to the bottom, okay? And then we have our heap invariant restored at that point. So just a little bit of an extra step. The logic is pretty similar. So let's go do some popping from the thing here real quick. So here's our tree. So let's say we want to get rid of 9. So we'll say extract max, okay? And I've got my kind of performance all the way on slow here, so it might be a little easier to see, okay? So 1 times k, that's going to be our easiest way to do this. So we're going to pull that out, swap with the last one, and then slowly bubble down with the largest, since we're dealing with a max priority queue in this case, okay? And we'll extract max again, okay, like so. 92, pick the biggest child, and then swap in that direction all the time, okay? Always max log 2 base, log base 2 of n, okay, to get us down there, worst case, okay? So that's the main idea, right? So relatively straightforward. If it's a min heap, we're going to swap with the smallest of the left to right, okay? If it's a max heap, we're going to swap with the largest of the left to right, okay? So because of that extra comparison, we have a little extra cost on the bubble down, right? So we got 2 of those we have to deal with on each bubble down, each potential bubble down. So our worst case is really going to be 2 comparisons per step times the number of steps, which is going to be log of n. So it's going to be 2 log n, still log n in terms of how we describe these kind of performances, because we throw away that 2, but it's still going to be kind of a 2, okay? Now, we're not going to really do this in our lab or our homework, but if you wanted to remove from the middle of the heap, it's a little bit different. So if you grab something arbitrary, we're still going to play this clever trick of swap and bubble. So if I want to get rid of the 8, I'm going to swap with the 4. And then I got to ask myself, okay, am I going up or am I going down? Well, if you think about it, we're never going to really go up if we were already in a valid binary heap, okay? So, because there's no way that 4 could ever be above an 8, right? So all we're going to end up doing is bubbling down, assuming we need to do that. So we get rid of that 8, and then we actually are going to just do the bubble down until we get that thing where it belongs. So that is kind of the answer to that question. We just had a valid heap array to start with, which is not always the case. We could have had a random tree and we're trying to turn it into a heap if somebody gave us a tree and said, here, fix this. But in this case, we knew we already had one. So it's a lot simpler process. Okay. So we won't do a lot of that, but that's relatively straightforward to do. Okay. And so there's our final fix. Okay. I think you can kind of do this one on yourself and kind of see what that looks like. You can slow it down. And there is a difference in this algorithm. I think it's this one. Yeah. So there are 2 implementations of this. So one of them is the one I just described to you, which is to say, I'm going to swap it with the rightmost one on the bottom row. The other approach is that I swap it with the root, and then I just bubble down from the root. So there's kind of two different ways of doing this that are kind of roughly the same. One's a little bit slower than the other, but it doesn't require as much new code. So if you go over onto this visual algo site and you see it doing something a little bit different, it's probably because they're using a different kind of strategy. And I think they might even have a bug, to be really honest with you. I could be wrong, but I think their remove of the ith item sometimes brings in a node that didn't exist before. So I think they might have a little teeny tiny bug on there. Okay. But we're not going to really spend a lot of time with that. We're just mostly interested in the vanilla kind of thing. Okay. So that is the idea of not only the binary heap, but the priority queue in general, right? And that's one of the most optimal ways we could actually do it. And the code for that is so compact. It really is about, if you write it compactly, maybe a dozen lines of code in the smallest implementation you could do. So it's not really worth us doing as an assignment or a lab, but we're going to do a small version of this with the lab today to make sure that you understand the equations we're using. But looking forward to our homework 3, we're going to try to implement this as a linked list. So bear with me for a second. So I take a small side trip to show you where we're going in the next 2 weeks. Most of you could jump on this tonight or tomorrow if you wanted to, without needing any other information regarding, this stuff. So let's just look at what we're going to do with homework 3. So you have it out there, and then we'll kind of come back to the lab and maybe get you out of here a little bit early today. So let's talk about homework 3. So about 2 weeks, it's going to be a singly linked implementation. There is no bonus. I thought I removed that, but I didn't get that slide set updated. So singly linked list, and it's up to you to figure out how you want to attack this problem. So you can push stuff in anywhere you want and pop it in any way you want, and you want it to be as optimal as you can. And, the hint is you'll never be as optimal as, a binary heap, but that's okay. I'm not grading you on your performance, grading you on your assessment of your performance in part. Okay. So a lot of the code has been started. We'll look at the code here in just a second, but let's remind ourselves of what we're going to try to do here. So our private data members of our priority queue class are going to just have a head pointer linked list with a bunch of nodes, and we're just going to push stuff in there. Now you can push it in and do what we would call eager push, which means you're kind of like the kind of person that cleans up their room all the time. It's like, okay, I know I'm going to need to get the biggest later, so when I push it, I'll do some work on the front end. So we tend to call that an eager approach, and this is an actual thing with algorithms. Eager approach. Or you could say, I'm going to deal with it on the pop side. I'm just going to take the easy approach, chuck it in the corner, and when I come back later and somebody needs the biggest thing, I'll go looking for the biggest thing. And that's what we call, of course, the lazy approach, right? And there's nothing bad with the lazy approach. Sometimes it's better than the eager approach, in fact. So you get to decide, which of those approaches you want to take to manage this performance of this data structure. So it's going to be through the push and the pop. It will be done via pointers, of course. And so we'll have to review our pointer stuff. And you can keep track of size kind of as you go, so you don't have to go counting that stuff. Okay. So that's really all it comes down to. So it's not a lot, just kind of a warm up again on pointers and nodes and stuff like that. So our data structure is going to kind of look like this. We're going to have a current size. We're going to have a head pointer inside of our private area, and then we're going to have our methods, and that's pretty much it. And I've pre-written a really aggressive unit test. So it's going to beat the heck out of your data structure and try to crash it by doing all sorts of things that, in theory, all of your push and pop will handle, okay? And you're welcome to look at all that code. I'll show you that here in just a second, okay? So again, not a optimal way, but it gives us an excuse to warm up our pointer stuff, which we're going to need a lot in the weeks ahead. So you might find it to be a good doable algorithm, but maybe a little bit of a way to shake off some of the dust on your pointers. So let me see. I think I want to dive back in. Oh yeah, just to kind of summarize this. A lot of algorithms use the categorization eager or lazy. There's another one called greedy, which is a little different. These terminology is a little confusing, but this kind of characterizes for you the eager, lazy approach, right? And it'll kind of warm you up to this idea when we look at some more complicated algorithms, okay? So you can decide how best to actually do that. So let me just show you the code real quick. We had a link back here, but you'll want to use the link on Canvas as always. And there's a Program IZ Pro, Replit, and online compiler links in Canvas now. So you can kind of choose which one you want to use. They're all pretty much the same kind of situation. Sorry for the bright lights there. So here's our node. That's kind of predefined. We've got a single pointer, right? Next connects them together. Value is the integer value. And if you just search for the to-do in here, right? If you look for the to-do with a control F, it's going to take you to all the places where you need to implement. Push, pop, get size is empty. And then the test me is down in main. So when you're ready and you've got all this stuff kind of implemented, all you have to do, you don't have to worry about the test me. You can look at it if you like. But down here in main, all you've got to do is uncomment that, and it will call that function and test that as thoroughly as I could, okay? Otherwise, this part is just an interactive thing that allows you to test it until you're ready to actually turn it over to the test suite. So you might want to leave this commented out until you're ready and you're convinced that you've kind of got this part working okay. Okay. So high level, that's 3 questions on that before we kind of move on to our lab for today. Okay, all right, very good. So let me cruise on down to our lab, which I think starts right after here. So lab 9, not bad. My favorite thing to do with a new data structure, print it, right? So we're going to have an array and we want to print it row by row by row as if it's a binary tree. Don't worry about lining things up, right? The root doesn't have to be in the middle of everything, but if you want to, you can try to figure that out. It's a fun little problem. But otherwise, just sort of print the, root, then 2 things, then 4 things, then 8 things. So you'll have to think about how you want to do that, given that you just have an array and the number of things that are in that array. So I'll leave you guys to sort through that one. And then print the parent of child, right? If I give you the array and the child position, you print out the actual parent that goes with that child. So this is just about you taking those equations from our slides today and just kind of hooking those things up. So not a lot of work, but hopefully it's enough to kind of build some retention in your memories about how all these things kind of fit together. Okay. And I think that's all we have. Yeah. So that's kind of the end of that. I don't think there's really a lot in here to talk about. You can kind of see, again, you search for the to-do, it'll get you to everywhere you got to be to implement some code. And it's very few lines of code. Okay. And I just put it in this format so you can kind of see what you're starting with, but you should end up printing out things that look pretty much like that, okay? Hopefully that is relatively straightforward for you all, okay? And that's it. Any questions before we call it a day? Get you guys out of here a little early. Okay, thank you very much. You guys have a good week, and I'll just hang around, of course, for any questions that people have on homework too. Okay, thanks.